One left more. No, no. I would watch like this was still about sleeping. This particular game.
Okay, looks like everybody's here, so let's get started. All right, so our next speaker is Binyi Chen, who's going to tell us all about lattice folding. Binyi, the floor is yours.
Yeah. Thanks. Can everyone hear me now? Cool. Yeah, thanks, Dan, for the introduction, and thanks, everyone, for coming. Today, I'll talk about folding scheme, which Benedict already mentioned on Monday, which his name is accumulation scheme. And today, I'll be focused on the construction folding scheme. And that folding scheme is a really powerful tool for enable very scalable proof system. And later, William will also talk about hash-based construction, but my focus will be lattice-based that are based on joint work with Dan, both of which I think is pretty interesting and useful. Okay, so let me start with some context and motivation. So as we all know, ZK SNARK has witnessed great progress in recent years for development and the speed. Every month, we have seen maybe a new scheme that is faster than before. And we also have seen many new advanced applications, such as ZKVM, proof of learning, data provenance. And all these new applications now require a very different task than before. We want to prove some really large-scale computation. For example, as Ron mentioned on Tuesday, in ZKVM, we want to prove, say, tens of millions of instructions in virtual machine whose correctness guarantees the safety of billions of funds behind blockchain. And there are many other applications as well that requires you to prove a really large-scale computation. And in that case, we have some new design requirements for proof system. First, we want long-term security. As development of quantum computing, we might want, if possible, to make it plausibly post-quantum secure. And second, we want it to be scalable. So it means as the statement grows, we still want the proof generation to be reasonably fast and memory efficient. And this is not that easy task. In the industry, many SNARKs, they are relying on, if not one, but more than one of these following algorithms and operations. And some of them, and all of them are not scaling that well, okay? Because some of them are having superlinear time complexity, and as statement grows, it will become more and more expensive. And some of them are actual linear time, but however, memory becomes a bottleneck in that case. You don't even have enough high-speed memory to run some algorithm on that large type of instances. So a natural question is it possible to make the existing scheme more scalable without designing any new system from scratch? Can we boost the existing proof system to be more scalable? And one approach is exactly what Ron has explained on Tuesday, is using recursive SNARKs. Okay? So as Ron mentioned on Tuesday, there is a system called SP1 Hypercube, which uses hash-based proof system and also the tree-based recursion to make it more efficient. It's very exciting and very good system, and it allows you to prove, say, more than 90% of Ethereum blocks in just less than 12 seconds. But there's a small caveat in that you have to use more than 100 GPUs, which is not that ideal. Okay? You have to use a lot of hardware resources, which makes this scheme, the system less decentralized. So a natural question is, can we meet the Ethereum Foundation's requirements? As Ron mentioned on Tuesday, it's possible to achieve the same thing, same throughput and latency using less than 30 GPUs. Or even 1 or 2 GPUs is impossible. Okay? So that's exactly the motivation of accumulation of folding schemes. We want to combine this idea with folding scheme so that we can obtain much faster, concrete, efficient system than using SNARKs or recursive SNARKs. So at a very high level, I'll explain how it works. This is exactly what Ron has explained on Tuesday, but in case anyone missed the talk, I'll just briefly mention again. So say we have some computation that's large to very large and very hard to verify. For example, you want to think about, for example, 100,000 signature verification. And a typical way to do that is split these large computation statements into many small chunks. For example, each chunk now may be responsible for just checking 100 signatures. Okay? And you have to extend this statement a little bit, which is some technical details that I won't talk too much about it. And then now it suffices to prove this collection of these many chunk statements. And turns out we can do some kind of folding tree and reduce the checking of these many statements into a root statements. Okay? So the proof of knowledge for this single root statement here is enough for us to extract actual witness for all the statement at leaves. Okay? And nice thing here is that the statement size of this blue box is not too much larger than a single chunk statement for checking the 100 signatures. And also, because it's much smaller, now it suffices for us to run this SNARK, which run in much smaller instances and leads to a proof much faster. But here's a key difference from the recursive SNARK approach, in that this folding scheme is way faster than SNARKs. If you look at real-world schemes, this elliptic curve-based folding scheme called NOVA is more than 100 times faster than elliptic curve-based proof systems. So potentially we might achieve much faster speed up if we use folding and replace recursive SNARK with folding. Okay? So this is the main idea on how you can obtain much faster concrete efficient systems. But I want to mention you cannot get around this kind of limitation, which is already in recursive SNARKs, because you have to instantiate the random oracle. Like our scheme is also in the random oracle model. You have to instantiate the random oracle in the statements, and you have to assume that it's secure. It's kind of a heuristic of heuristic, which I'm also not very comfortable with. But this is not focus of today. We will consider a much cleaner primitive, which is this public coin interactive folding scheme. For simplicity, I just consider public coin interactive case. In this case, we have much cleaner picture. And we can even build the schemes in the standard model without any random oracle. Okay, so I will just for simplicity focus on that. And any questions so far? Okay, so I think Ben already mentioned this definition, but I will quickly review it again. I find it extremely useful and important to first introduce this notion called the reduction of knowledge before defining folding schemes. And this is a primitive introduced by Kosapali and Brian Parnell in 2023. So essentially, this is a public coin interact protocol between the prover and the verifier. And the goal here is to check certain instances is in some relation R1, which we call input relation. And at the end of this protocol, if the verifier accepts, the verifier will convert instance into a new instance, X prime. And the prover will convert the witness into a new witness, W prime. And if this protocol succeeds, and finally we reduce the problem of checking something R1 into checking something R2. And this is called the reduction knowledge from R1 to R2. And it also satisfies some similar property like non-interact argument knowledge or interactive argument knowledge. Like completeness means that if the input is in the relation, the output is in the relation after all this execution. And second, knowledge soundness means if there exists some malicious prover that's able to provide a instance and also convince the verifier in this protocol, and in the end also provide a valid witness for the output instance, then we can extract a valid witness for the input instance in relation R1. And finally, succinctness just means the communication of this protocol and the verifier's complexity is sublinear in the witness size. So if you look at it, this succinct argument of knowledge is just a special case, while the R2 is just this very trivial relation that basically checks nothing and has this singleton. But this is more general than that because we can set R1 and 2 yourself. Okay? And another very nice property about ROK is that it's composable. It means that if you have ROK from R1 to R2 and another one from R2 to R3, you can compose them together and get one from R1 to R3. Okay? This is proved in this paper, and it's not too hard. And also, by the way, this composability is generalized to compose for arbitrary number constant steps. Okay, this will be very useful later. Okay, now I'm ready to define what folding scheme is, which is just a special case of ROK. In this case, the input relation is just a product of two relations. One is a statement called inside RMP, which is this MP-complete relation that's used to capture the real-world computation. Okay, and the second relation is called accumulated relation, and the statements is corresponding, we call it accumulate statements. And in this case, also I want to mention, typically in practice, this instance of RMP also contains a short commitment to the extended witness. These are without loss generality. We can always do that by adding a commitment to the extended witness. This makes folding much easier.
By extended witness, you mean W1 and W2?
Oh, it's just like our CS statements, the extended witness.
Oh, just like the tableau.
Yes. And our goal here is to reduce the checking of these two statements into a new statement in our ACC. Okay? And this new statement is called folded statements. And you can see this is actually a weaker task than SNARKs. Why? Because in SNARK, we have to prove everything in one shot. We will need to provide a really short proof in one shot, and which is sublinear. But here, we can merge the checking of two statements into new statements, but this new statement might be still linear. Okay? It's just from 2 to 1 rather than from n to log n or sublinear. So that's also the reason why in practice we can obtain much faster folding scheme than SNARKs. Okay? And also proved by these papers, the folding scheme is already enough for us to obtain the piecemeal SNARK in the previous framework by combining with another SNARK that run on much smaller instance. Okay, any questions so far?
Sorry, I have a question.
Yeah.
So you're saying folding is for sure easier than SNARK, because SNARK, the fold, you get something that's still difficult, just a little less.
Yeah.
That I understand.
Yeah.
But then you're saying, oh, here's a way to construct the SNARK, just fold and fold and fold and fold and fold until you get something easy.
No, and finally you still need to use a SNARK. So in the previous one, in the last step, you still need to run a SNARK here.
Okay.
Yeah.
Okay, because you don't get, oh, good.
Yeah.
Okay. But I guess my question, why I understand why folding is definitely easy, is the reason that folding again and again and again until you get like this thing SNARK is more efficient. Is because you're basically doing kind of linear many foldings?
Yes, I'm doing just even just constant unfolding in practice. You should go from some really large statements into like 10 times smaller is already really good. Right?
I see.
In that case, SNARK is already sufficient. Yeah. Yes. Okay. So that's the definition, and hopefully now I'm convinced you that why folding is very useful in practice. And now the question is how to construct one. And my focus today will be on lattice-based construction. And why I care about lattices is because it has 3 really nice features. First, the proof is extremely fast. This might be surprising, but I want to convince you this is indeed the case. Particularly, like the proof complexity is nearly as fast as just committing to the weakness of this relation. And this is something that's much harder to achieve in a SNARK world. Well, in SNARK world, beyond just committing the weakness, you need to do some more heavy machinery, like proximity proof, polynomial opening proofs, and so on. But here it's much easier and can be much faster. And byproduct is that in this setting, you also, if the witness is sparse, you don't need to pay any cost for those 0 elements. Okay, this is another nice feature. And second is this plausible post-quantum security, which is kind of really obvious, even though we don't have very formal proofs. And finally, it has very succinct verifiable. This is something that's kind of more competitive than hash-based systems. Like hash-based system also has very fast prover, but usually verifies less efficient. But in this case, lattices can have very succinct verifiable. And even better, this case scenario is even better than lattice SNARK world. If you want to build a lattice SNARK, usually we don't have a really concretely efficient scheme that also have polylogarithmic verifiable. Recently, we do have some new works that has polylogarithmic verifiable, but it's not that concretely efficient. But in folding world, we can achieve best of both worlds. We can have really nice asymptotical complexity and also extremely concrete efficiency. So that's the reason why we want to study it. And let me start with some state of the art. Like, let's see what's the current best scheme that we can find. Also, I want to mention in this lattice world, it's slightly different from hash-based system or elliptic curve-based system. Well, I would say this first-class citizens is actually a quotient ring rather than a field. So this is RQ, which is CQX, divided by this idea of x to the d plus 1. Well, Q is some small prime, and d usually is the degree of the polynomial is something like 64 or 128. And we'll build on based on that, because if you work on field, it's less efficient than other parts. But if you work on this quotient ring, it turns out lattice can actually be extremely efficient. Okay, so the current most efficient scheme is kind of combine the 2 orthogonal techniques from 2 recent papers. One's from Lattice4Plus, and the other one's called NEO by Srinath and Wilson. Okay, and it allows you to do the following things. First, the corresponding NP relation is able to capture simultaneously proving d different R1CS statement over small field, each of witness size about n. Okay, so it's very good for doing batch proving, where d corresponds to the degree of these quotient rings. And we are able to fold these kind of statements in prover time about n lambda log d field multiplications and n d lambda field additions. So if d is kind of approaching lambda, this is like amortized-wise, this is really good. And even better, it's extremely or even embarrassingly parallelizable, and that makes it very hardware friendly and GPU friendly. And this constant overhead behind it is also very small. And the verify is also pretty good. If you want to do field Shamir and make it non-interactive, the complexity is about lambda plus log n small field hashes. And additionally, you also need to pay another d operation over these quotient rings. Okay?
So then you want to think about how I should be doing the prover here. So
Oh, yeah.
like in hash-based things, wouldn't it be more like n or like with fast code it would be n field operations. Here it's n times lambda.
Here's n times lambda, yeah, n times d, something like that.
So
when
it does appear symptotically to be a bit larger.
So when d approaching lambda, this is about log lambda field multiplication and lambda field addition, which indeed is slightly larger, but it's highly parallelizable. And if you forget about addition, this multiplication is actually very competitive. Like log lambda per field elements is really small.
So slow down. So here I'm seeing.
So this is the size of data size of n times d rather than n.
So log d I don't care about. It's really small, right? So it's n lambda. It dominates, but it's n lambda field operations versus n-ish field operations or extension field operations, maybe in hash-based system.
In hash-based system, what's the witness size? Is it n or n lambda?
I'm thinking of n.
But here is n lambda because we are actually.
Because up here you're already batching.
Yes, yes.
Is lambda a statistical security
Oh,
parameter, or?
So lambda as security parameter is actually like similar to lattice dimension. So kind of is larger than 128, like 500, something like that.
Should just be d then.
Why is d? D is not the dimension of lattices. D is smaller than like dimension of lattices. Of course, if you ring sys, then it's lattices dimension, but like in practice, we won't use that large d for some efficiency reasons.
A question?
Yeah.
When you write this many FQ hashes, do you mean the number of FQ elements you need to absorb and squeeze?
Yeah.
Or just squeeze? Like
Yes, yes. Like,
absorb and squeeze.
yes. Like times some constants, like small, very small constant.
Thank you.
Does the complex? So here you explain what RNP is, but does the order relation also matter? How it looks like? Because that's the one you're gonna at the end need to have a SNARK for example.
Order of relation.
No, the other, the RACC.
Yeah, that one is similar to that.
It's similar. I see.
Yeah. Okay, and any questions? Okay, and the security relies on this module SIS assumption, which is an adaptation of SIS in the module setting or ring setting. So now it's kind of a standard assumption for those applied lattice schemes. Okay, and also there's an open question here, which I want to ask those quantum crypto guys to help. We don't know how to, when we do the field Shamir, we don't know how to analyze security in the quantum random oracle model. So it's not safe to say it's a post-quantum secure even in the random oracle model. And it turns out to be really hard to analyze, and I leave it as an open question. Okay, so.
Do you know how to analyze it in the classical case with state restoration, soundness, and do that problem?
This is different thing. This is
There's
not.
no issue there when you piece everything together.
In hash-based, I think there's no issue, but I don't think if you have rewinding, it's kind of like a little bit more complicated.
I think it looks like a elliptic, right? It's not trivial.
Yeah.
I thought the question was about classical.
Yeah, I'm asking about classical. Whether you
I see. You mean classical security in ROM?
Yeah.
Oh, our paper actually doesn't have it, but in that case, I think shouldn't be too hard. Yeah.
The classical
Yeah.
How many rounds do you have in your reduction?
hash-based post-quantum or
Reduction, we only have constant. Reduction only has
Yeah.
two constant ROM. Like
And
two
for
round
these
one.
constant rounds, did you try to do a round-by-round analysis, or it's just like a regular soundness?
Regular soundness. Yeah.
Okay, then a starting point would probably be to look at the
In ROM, you mean? Or
no, I mean round-by-round analysis
Oh, I see.
of classical,
Right.
right?
I see.
That would, and then actually, I think in the CMS paper and the QROM, I think we have some statement there one can extract that roughly says if you have something that is classically wraparound sound, then the corresponding thing is secure in the QROM under Fiat-Shamir. So it would be enough to show wraparound sound.
I see. Okay, yeah.
But here you have like lattice assumptions in the middle, no?
I understand, but like you're still proving a classical wraparound soundness.
Well, you won't get round-by-round soundness, right? Because it's an argument.
Yeah. Soundness.
Yeah, but like round-by-round soundness is a
Okay.
Okay, fine. No problem.
Okay, nice. So the rest of the talk, I will organize it as follows. So first, I will review this framework for doing the folding using linear homomorphic commitments, and I'll see some challenges when in this lattice world, and then finally, I'll address challenges using the range proofs in the lattice setting. So in the lattice setting, we will use this kind of framework that adapts from hypernova. So we have two statements. One is in this NP-complete relation that usually consists of multiple quadratic equation, and another statement is on RACC, which I haven't defined yet. I'll define later. And the first step is to linearize this statement in RMP into a new statement in RACC that becomes linear. And after that, we merge these two statements into one using some folding operations. And today I'll skip the first step, which is kind of standard trick in the community using sum check, and I'll focus on the second step, on how to merge two accumulated statements into one in the lattice world. So this is a kind of simplified version that can be transformed from RMP into accumulated relation, but it's already covered all the key concepts. So if you look at it, the instance consists of a short commitments to the witness, which is first is very short string, and second is linear homomorphic. And the statement is true if the following holds true. First, the witness is the correct opening for the commitments. And second, this Martini evaluation statement holds true with respect to F and this public Martini evaluation point. So you don't need to understand what Martini evaluation is. You just need to understand that it's basically just inner product check between this witness F and some tensor vector derived, which have length n derived from these log n values. Okay? So now you have two statements in this relation you want to check, and you want to convert them into one statement. The first step is to run an ROK that unifies the evaluation point. I won't talk about how to do that, but after that, you will get two statements now that share the exactly same evaluation point. But why we want to do that? The key reason is that after doing this, these two statements now share the exact same system of linear equations. If you look at it, this inner product check we have here, the linear combiner of the witness is exactly like corresponding to evaluation points. If they are the same, this is exactly the same linear equations. And that means at this point, it is OK for us to just randomly combine the witness vector. And if the input statements are true, the out statements would also be true. More precisely, what we do is the prover will correspondingly combine the witness using some random combiner. The verifier will combine the corresponding commitments, which are linear homomorphic, and as well as the evaluation values. And if any one of the input statements is false, with high probability, this output statement will also be false. This is kind of an intuition for soundness, but I don't talk about non-sounds yet. So this is kind of framework we would do, but now the key question is how do you instantiate this framework in the lattice setting? The first question you need to solve is that how to instantiate the commitments in the lattice setting. Remember what we want. We want a short commitment string. We want this linear homomorphic. Okay, and a very natural candidate is this anti-binding hash functions. Well, you have some message. For simplicity for now, let's just the integer vector of length n for which there are no norm. And you can compress this long vector into short string by multiplying this like random and narrow matrix and compress into very short string. And I want to mention also with some easy tricks, which I don't want to have time, I don't spend too much time to explain, but you can even support even higher norm input without much problem. But for now, for simplicity, I just assume the message is no norm, just for simplicity of explanation. Okay, at this point, this is not our first-class citizens. This is over ZQ, and it's not very efficient. Okay, you cannot use this to compete with other type of schemes. But if you use a ring-based variant, this will be much more efficient. And this is a Swift that's proposed by Vadim, Michel, and Piker, and Rawson. So the idea is very simple. You just replace these integers with this ring of integers, ring of integers of second fields, and also replace CQ with these quotient rings. And you can understand just add some set of polynomials that support additions and also multiplications, modulo x to the d plus 1. And they all have degree less than d. And now the key point here is that because the degree d is larger, it also contributes to the lattice dimension. Okay? So in that case, we don't have to set the number of rows of A to be lattice dimension. We can make it much smaller. In the extreme case, in the ring C's case, you just set this kappa to be 1, and this is just an inner product check, inner product computation between two ring vectors. But why is that more efficient? The key reasons is first, using some nice encoding, you can pack many ZQ elements inside one polynomial. And second, you don't have to pay this matrix vector multiplication. You can use NTT to do much faster ring multiplications. So amortized-wise, the commitment cost for every ZQ element now is about log lambda field multiplication versus lambda multiplications, which is significantly faster. And in practice, they are like 30 to 40 times faster than Peterson hashes that are based on elliptic curves. Yeah, question?
How much time does the backing take? Is it linear in D? Is it like?
Yeah, it's linear in time, or actually it could be even free using some nice encoding from like this Neo paper. Yeah.
Question?
Yeah.
Do you have a sense of how does it compare to hashing the same amount of data?
I think it should be. I haven't run benchmark code. I think it should be similar, and hash might be slightly faster than this. I think.
You're saying that it could be comparable to doing like a Merkle tree on the
yeah, it's slightly slower, but it's comparable. Okay, good. So this is very promising, but it's not a perfect scheme. Why? Because it's actually not strictly linear homomorphic. Because if you remember, we actually require this message to be no norm. Okay, this is very essential for its binding property or for having a reduction from SIS. And that means this binding holds true only if the witness is no norm, and this adds a lot of complexity when you do the random combination. You have to control the norm when you do the random combination, and this makes things much more complicated. Before explaining why it's complicated and how to address it, I also want to mention another open question. If you have a really nice lattice-based commitment that says all the property I want, first it's very short output, it's linear homomorphic, and if it doesn't have any norm constraints, it's just simple as Peterson, then you can leave now. You don't have to waste the next 30 minutes with my explanation and all the solution. And they will lead to very simple schemes. But it turns out this question, I think, is even harder than addressing this question. So I don't know how to do that. So this is also another open question. So now let's assume we do have these norm constraints. And let's see how to address the issue and what's exactly the issue. So the immediate issue here is the norm blow up after random combination. Let's consider a naive case. Starting from now on, let's set up some metric and always consider infinite norm. Okay, that means the maximal absolute value of a vector, and also denote ZQ to be represented by this minus Q half and Q half. And if you use a naive way to do random combination using a scalar over ZQ, then on the one hand, you have to set Q to be large enough because the chance set has to be large enough to have really small soundness error. And on the other hand, if you set Q to be too large, this norm blow up is really bad. Okay, it's as large as Q. So this is pretty bad, and the norm immediately go beyond the bound we can afford. So this is not good. In practice, actually, we'll come back to our first class reasons. We'll always work over polynomials. So the challenge will be those set of polynomials that has really small coefficients, like -1, 0, and 1. Okay, in that case, we consider everything over the ring, and we do all the arithmetic over the rings, and we sample this challenge over this set S. And on the one hand, this set now is much larger. It's like 3 to the d, which is exponential to the security parameter if you set the degree of polynomial large enough. On the other hand, because it has really small coefficients, the norm blow up is actually only about the degree of the polynomial, which becomes lambda. So this is significantly better than before. Okay, but this is still not good enough in folding setting, because after every folding step, the norm keeps increasing. In order to support enough number of folding steps, we have to set the parameter really large in the beginning, which kind of snowball effect makes the scheme less efficient. So the question is, can we fully eliminate this kind of norm blow up? Can we have no norm blow up? And the answer is yes, and it's actually a very simple trick that's widely used in homomorphic encryption. and it's called decomposition trick. So to make my explanation easier, let's consider a norm bound in these statements. Okay, we add one more bound, and it's saying that this witness should be having norm even lower than B. Okay, and now if you do one round of norm random combination, you obtain a faulty witness that has slightly larger norm than before. But now we can correct its norm using decomposition. The idea is you have a large value. You can split one large value into high order bit value and low order bit value. Both are much smaller than before. And you can extend this trick to vector or even vector polynomial by decompose coefficients element-wise, right? So basically, we can do this. Like this is basic reduction knowledge. Where the prover, given the knowledge of S star, he will decompose it into F1 bar and F2 bar that satisfy this notion, this relation that has much lower norms. And then he will send two commitments to the verifier, which is the commitment to F1 bar and F2 bar. So CM1 bar, CM2 bar. And the verifier will check the consistency between these two commitments and the input commitments via linear homomorphism using this relation. Okay? And after that, it suffices to check these two statements are true now. If these two statements are true, then we can, given the this knowledge of F1 bar and F2 bar, we can recover the value of F star. So this is reduction knowledge. And at this point, now we add another round of folding. We obtain a new folded witness whose norm bound is about lambda 1/2 times square root B. Okay? And if you set B to be appropriately, you can make this even smaller than B. Okay? So that means, in sum, what we have done is that if you compose all things together, we have successfully converted two statements into one statement where the norm does not increase, maybe even decrease. So this solves the issue of norm blow-up. However, this is only the half of the story, which is the easy part of the story, that it only solves correctness gap. It allows you to convert two statements into one without increasing the norm, but there's no way that you can prove it's a reduction knowledge. You don't even know how to prove this first step is reduction knowledge or not. Because given this output, you don't know whether you can extract some input that have even lower norms. So this is the key issue. And let me see why it is the case. So let's consider the second challenge. How do you do knowledge extraction in this protocol? So in verifier's view, you can see here that given the two inputs that's received by verifier, what it does is just send like sample random combiner and compute a commitments. And knowledge sounds is saying that by maliciously chosen CM1 and CM2, if the prover is able to later provide the correct witness for the output, then you should be able to extract a valid witness F1, F2 for the input commitments that have even lower norms. Okay? But how do you do that? There's an easy approach that doesn't work, but that's very useful to give an intuition on why it's hard. So the idea is to do rewinding and interpolation. So let's see, for simplicity, let's assume the malicious prover is deterministic and also always successfully provide a valid opening in the end for the output commitments. And in order to extract witness for CM1 and CM2 as commitment opening relation, what we can do is can sample two different challenges and call this malicious prover. And the malicious prover will provide you the valid witness for the output commitments. Okay, and that is relatively low norm. And you can assume the FG are some correct linear combination of the things that you want to check, want to find. And you can solve linear equations and find the candidate witness F1, F2 for CM1 and CM2 that satisfy these linear relations. Okay, but there's two issues now. Can anyone see what are the issues? Like we even have a really close formula for that. But this is not a well-defined solution. Why? Because remember, we are choosing alpha beta from polynomial rings rather than a field. So there is no guarantee that the difference is invertible or not. Like not every non-zero element in a ring is a unit, is an invertible, is a unit, right? So they may not even exist over the ring. And second, even we know how to solve that, it does not guarantee any norm about F1, F2. They might have large norms. So let's see these issues one by one. The first is the issue is how to make sure the differences are invertible. There's a naive idea where you just carefully choose this set S such that differences are always invertible. This is by definition correct. Unfortunately, we've proved that this kind of set is never too large. It's really, really small, which affects the efficiency of soundness. Okay? It turns out a much better approach is to relax the definition of inverse. Well, you carefully choose the set S, such that the difference might not be invertible over R, but invertible over the quotient ring RQ. This turns out to be much easier to construct by Vadim and Greg. They show that we have exponentially sized set S, where every element is no norm. That is invertible over RQ. So at this point, we can set all these linear equations over RQ rather than over R, and we can solve this linear equation and get some kind of witness over RQ. Okay, this is solvable. And then we can lift back into R by just using this canonical lifting, by mapping this minus Q half to Q half into integers. And then let's hope for the best that there are no norm. But indeed, there are not no norm. So this comes to the second issue, in that after this extraction, you extract some valid witness that satisfy linear conditions, but they are not no norm. Okay? So now the question is how to make them no norm. And this turns out to be really hard questions if you don't do anything here. Okay? And it's very hard to get a correct knowledge extraction. And the natural fix is just add one more proof, like add a proof of knowledge, showing that I know some proof of openings, that moreover they are like really no norm. But there are two requirements in terms of efficiency. We want these added machineries to have negligible prover overhead than before. Then it's really naive and simple solution. Okay? And second, we also want the verifier to be as small as possible. And our goal is to achieve like logarithmic time complexity. And this is what we achieved. And later, later I will explain two approaches for that, which are based on range proofs. Any questions so far? Cool. So before explaining how to do this range proof, let me digress. Oh, yeah?
So this limiting the challenges space is that technique that they call like CWSS, like coordinate-wise spatial soundness or something?
That's different. That's kind of different. That's a strategy to do the knowledge extraction.
So that S is also used in...
Oh, yeah, S is also using that. I mean, almost all the efficient protocol is using that kind of S, or different set of S, but they're all polynomials rather than scalars. Yeah. Mm-hmm. Okay, so before explaining how to range check ROK, let me digress a little bit and review this notion called zero-check relation that has been observed by many previous work, but recently it has been formalized by this Hyperplonk paper. So the zero-check relation is the following. So in this instance, it involves k different commitments. And the witness is a matrix where it has k columns. Each column has length n. The statement is true if first, every column is the correct opening for the commitments. And second, for every row of the matrix, this certain algebraic function g will evaluate to these row values to 0. And typically, this algebraic function g is some polynomial that's degree less than some small constant and also degree larger than 1. And it turns out there's a by the way, there are several examples for how you can set g. For example, you can set it to be the sum of square of the row values, or you can set it to be some quadratic equation over the row values. Okay, it doesn't have to be a single value, it can be even a vector. And it turns out there's a very simple reduction knowledge that translates this zero relation into a much simpler relation that is folding friendly. That means if you do random combination, it still works. And this is using sum check. Okay, and it has really efficient prover and verifier. And for now, let's forget about this, how you instantiate this ROK. Just assume there exists some really nice ROK from zero relation to this linear relation. That will be very useful later. And if you have any other better ROK than sum check, you can use that as well. So now let's get back to the task of doing range proof ROK, which is the reduction knowledge from this range relation to a much simpler relation. So this range relation, for simplicity, let's consider this form, where the instance is commitments, and this is inside the relation if the witness is correct opening, and moreover, every element of this witness is between this range, 0 of 2 to the L. And here I'm doing some simplification. So in general, this F is actually a ring vector, but here for simplicity, I just assume it's integer vector, which is much easier to explain. And second, we can also assume this range is arbitrary range. We don't have to restrict to this. But also for simplicity, let's just assume this is the range we care about. And our goal is to reduce this relation into a much simpler relation than only check linear evaluation statements. It's in the proc check. The reason we want to do this is because after that, we don't have any strict range statement anymore. And after that, it's much easier to do random combination and prove the reduction knowledge. We'll see that in a moment. However, I want to mention that in the lattice world, this is slightly more subtle, because depending on the instantiation of commitments, you always have some relaxed norm constraint in this commitment open relation. Otherwise, you cannot reduce to cis. But this relaxed norm constraint is much higher, like the bound is much higher than the bound here. So usually that should be fine. OK, this is the background. And now what's how to solve the issues? Like I will first explain this first approach by lattice fold, which allows you to reduce this relation into a linear statements. And the idea is the following. It consists of several sequential steps. The first step is an ROK that decomposes the vector into L different vectors. Okay, the idea is that you decompose this long vector into L long vectors that now become binary. So that this is basically a base decomposition of original vector. The reason we do that is we want to reduce it to a very simple zero-check relation. Well, to do that, the prover just send the commitment of Fi. The verifier will check consistency of CMI and CM using this linear relation. And after that, it suffices to prove the opening of Fi such that they are binary. And how to prove they are binary is just a very simple degree 2 algebraic relation, which is the algebraic function we use here. Okay? So as I said before, we have a really efficient zero-check ROK from that leads to this linear combination, linear evaluation statements. And after that, there's no strict random statement anymore. And we can do random combination using no-norm challenges and merge them into a single commitment and a vector. And after all this, we convert these statements into these statements. The things remain to prove is this reduction knowledge, right? And it's nice to see this as two sequential steps. Well, the first step is this reduction knowledge from range relation to decompose zero relation, which is actually pretty easy. As I said before, you have some vector that's binary. You can combine them together and you get a witness opening for the range statements. So that's the easy part. Let's focus on the harder part and more interesting part, which is this zero relation to linear relation.
Somewhere after doing the range check, you have it's supposed to be up to 2 to the L. You decompose it into bits, check that it's bits.
Yes.
You're happy.
Yes, I'm happy, and then do random combination. Yes. And the key question is why this is reduction knowledge. This is actually not that trivial, even though it's not too hard. So for simplicity, let's just assume L equals 2 and assume P star is deterministic and always succeed. Just for simplicity.
So, sorry, the decomposition has like an L overhead probably, and that's okay.
Oh yeah, that's a good point. I will mention that later. Yeah. Okay, so the idea of extraction is that given this CM1, CM2, we'll just run this previous naive rewinding structure again, and we get some candidate with F1, F2, and R is some randomness we use in this zero check. And at this point, I have no guarantee on the norm of F1, F2, but I want to argue that they are indeed no norm. Why? Consider this mental experiment where we run this rewinding structure again by using freshly independent randomness. At this point, we can get some new candidate with F1 hat, F2 hat, but there are no norm guarantee, so they are not even bound to the commitments. So it's possible that they might be different. Okay, F1, F2 might be different from F1 hat, F2 hat. But fortunately, according to our idea of the rewinding relation, this F1, F2 has some special form. The numerator vector and the denominator scalar, they are actually somewhat no norm, even though it's like strictly no norm, that's relative no norm that's secured by cis. So if they're that different, okay, then we can find this particular vector that is no norm and non-zero that solves MC's problem. So this will break MCs. So this should happen with low probability. And then if they are the same, then this is something really nice. Well, F1, F2 is independent from sampling randomness of U, and they also satisfy certain evaluation statements on F1 hat, F2 hat, and they're the same. So that means with high probability, F1, F2 satisfy zero-check relation. So they are binary. So this finishes the proof. Okay, so we are successfully extract something that are indeed binary and satisfy our input relation of L0G here. So it turns out when L equals larger than 2 and P star succeeds with non-negative probability, the analysis is more subtle, and we need to use this coordinate-wise special soundness plus some other techniques. Okay, so that's the first approach. And as Ron mentioned, there's an issue here. Okay, there's an efficiency issue. Right? Whenever you want to rank check one commitment, we have to pay L more commitment cost, which is pretty large, especially if L is large. So the question is, can we make a range proof as efficient as just committing to a single witness? And this is our second approach. Okay? And this is the approach from Lattice-based Plus. Before that, any question? Okay, so the second approach, before I explain how to do range proof, let me take one step back. And let's consider a more general notion called table lookup arguments. So table lookup arguments is saying to proof of knowledge of some committed vector f, such that every element of f now is within some public table T. If you set table T to be 0, 1, 2, 3 to d minus 1, this is essentially a range proof statement, right? So it's more general than range proofs. And you can rephrase these statements as the following, which is saying that for every index j, there exists some index delta j from 0 to d minus 1, such that the delta j's element of T equals fj. This is equivalent to say that fj is inside the table, right? So why we care about these statements? Because in this statement, you see I only introduce one auxiliary vector rather than L auxiliary vector. So if I have some way to translate this idea into proof, that might lead to better efficiency gains. And now the key question is how to simulate these kind of shifting operations using algebra formulas that is easier to prove. Because you know here, this is not algebraic. And those non-algebraic relations is much harder to prove using ROK. And our goal is to translate these kind of statements into better statements that is simpler to prove. And this is exactly, again, we'll come back to our first class decisions. We need to use polynomial to simulate the shifting using polynomials. The idea is simple. Basically, here I define a new quotient ring, which is RQ bar, that's this ideal becomes x to the d minus 1. Though I want to mention that the real scheme should be use RQ. Like this RQ, you should never use in practice. This is not secure. The only reason I use this is for simplicity of explanation. And if you choose this quotient ring, and then if you embed this table T into the coefficient of these polynomials, which is public polynomial that map every element Ti into the coefficient of this public polynomial, then we can do something simple. Okay? The key idea here is that key observation here is that in this quotient ring, we have some really nice structure where x to the d is equal to 1, equivalent to 1, because x to the d minus 1 is equivalent to 0. In that case, if you multiply some monomial x to the d minus I to this polynomial t, then this term will cancel out. The constant term will be exactly ti. So it's kind of a way to extract one coefficient from polynomial using multiplications. So now you can translate these statements into these statements. This is exactly equivalent. It's saying that I know some monomials inside this finite set, such that fj equals the constant term of t times these monomials. Okay, is that clear? So this is the same thing as this. Like if I want to prove that fj is in the table, fj equals t delta j, suffice to prove I know some x, these monomials, such that constant term relation holds. And nice thing here is that it's algebraic. So it turns out we have a really efficient way to reduce these range statements to linear statement now using this kind of approach. The idea is the following. So the prover will first send this helper information and commit it, and send it to commitment, send it to the verifier. And the one thing to note here is that this commitment is extremely fast to compute because the witness is extremely structured. It's very sparse and only has 0 or 1 coefficients. And this act turns out to be extremely parallelizable and way faster than regular sweep committing. So this is almost negligible. And after that, it suffices to prove this relation, which by the previous explanation, we just prove an opening of f and g for commitment cm and cm delta, such that fj equals constant term of t times the gj. And every gj is inside this special finite set of these quotient rings with degree less than d minus 1. And if you know a ROK from our lookup relation to linear relation, then you are done. Okay? So the question is, how do you generate reduction knowledge from this lookup relation to linear relation? And if you zoom in this relation, there are 3 key tasks. First is translate this constant term check into evaluation statements. And second is translate the monomial set check into evaluation statements. And finally, we want to merge these 2 commitments into one. Okay, that's our target goal. And turns out these two statements both can be efficiently reduced to linear evaluation statements. And after that, because they are folding friendly, we just do random combination and merge them into one statement. And that's it. So now the key question is, how do you translate this kind of constant check and monomial check into evaluation statements? Any questions so far? Yeah?
I may have missed something. Why is the table, like lookup table size D?
Oh, yeah. Let's just assume it's D for simplicity. Let's assume the range D equals 2 to the L. Let's for simplicity, just assume D is equal to the L. So in that case, they matches. But it turns out we can even support larger table, even if the table size is not D. But that's some kind of other techniques. Let's for simplicity just assume table size is D. Okay? Yeah. Any question? Okay, so now let's see how to, still have some time. So let's see how to reduce this relation into linear evaluation statements. The first one is check this constant check, which is the easy part. We want to convert this into evaluation statements. The key insight is here that what we want to check is basically some n different equations, right? We want to check fj equals the constant term of the multiplication of two polynomials. And if you have n equations to check, the natural idea is to do a random combination of this n equation and compress it into one equation, right? So what you do is do a random combination to the left-hand side, and the proof is the same as a random combination of the right-hand side. And here we are using some structural random combination, which have this really strange form of tensors. So it reduces to this kind of inner product check. And I claim this is equivalent to check the following equations. Well, the left-hand side is the same as this by definition of Martini evaluation. And the right-hand side is slightly different. If you look at it, the left-hand side is constant term function is applied inside the inner product. And the right-hand side, the constant term is applied outside this inner product between G and tensor R. But this is fine because this constant function is a ZQ linear map that maps to a degree less than D polynomial to a constant terms. If you do a linear combination of constant function, it's the same as constant function of linear combination of the corresponding polynomials. So this holds true. So in that case, this leads to a very simple ROK, where the prover just sends the evaluation of FR and GR, which is VF and VG, to the verifier. And the verifier just check this equation, which is very simple. And then after that, it suffices to just check these two linear evaluation statements for F and G. So these are linear evaluation statements. That's what we want. So this is the idea of converting constant relation into linear evaluation statements. So that's the first trick. And the second trick is how to convert monomial check into evaluation statements. Essentially, we want to check for every j, this gj, which is a polynomial of degree less than d, is inside this finite set. And how to do that? The key observation is that we can lift this polynomial of degree less than d into a much larger space first, which is this dqx, that no longer has its modulus x to the d minus 1. Why we care about that is because after that, it suffices to prove this lifted polynomial is inside this infinite monomial set of x 0, 1, x to x to d minus 1, x to d, and so on. And if it is inside this set, then before the lifting, this polynomial of degree less than d must be inside this finite set. Okay? And the reason we care about this is because this is much easier to prove. We have it is equivalent to check polynomial identity for that. So this holds true if only if this holds true. Well, here is the square of the gj hat x equals gj x squared. So if you look at some examples, like x, the square of x equals x squared. And if there's something outside this set, like x plus 1, square of x plus 1 is x squared plus 2x plus 1, different from x squared plus 1, as long as that 2x is non-zero. But to prove it, it takes some it's not a very trivial proof. And also I want to mention this is not holding true over RQ. So this is the reason why we need to do the lifting here before proving this. And you can trust me, this is true, even though I won't have time to prove it. And after that, we can reduce this polynomial identity check and collapsing it into a much simpler check over ZQ by compute the evaluation map of this polynomial at the point alpha and alpha squared. And this is some zero check-like statements over two vectors over ZQ, where the first vector is GJ hat alpha and the second vector is GJ hat alpha squared. And this is also over a small field that can be very fast. By the way, at this point, I assume Q is some large prime, like 128 bits. But later I'll mention that actually we can extend to smaller modulus as well. And after that, you can trust me that there's a very easy way to use the sum check again, which is very fast sum check, to reduce to a Martin evaluation statement for G at some random point R over ZQ log n. OK, so that's the basic approach. And after combining this and do random combination, you can get target statements you want. But this is only a simple version of our solution. Our actual scheme is actually more complicated than that. So first, we need to support a much larger Rome ranges than 0 to D. This is what your question is. And second, we also need to support this different ring, quotient ring. And this actually is not that hard if you just use some decomposition ideas that can be solved. And also, you need to support smaller modulus Q, which needs to use some tricks over extension field and tensors. And finally, I want to mention these things. This is something that's more subtle. So in practice, we have to commit to some ring vectors to fully exploit the power of these swift commitments, right? We shouldn't just commit to integers. We should commit to polynomials. So we actually need to rank check every coefficient of this vector of polynomials. And that turns out to be a little bit more tricky. And we need to use some more techniques called double commitment folding to solve this issue and make it extremely efficient. But I won't have time to cover that, I think. Yeah, you can like discuss with me offline for that. OK, so that's basically it. I think I'm right on time. So summary is, I think folding is a really, really great tool for boosting the SNARKs to be more scalable. It's really promising, even though there's some kind of security hope behind it. But like in practice, it's really promising. And the second, I found that lattice-based folding is also very promising. It's much easier to build than the lattice SNARKs, and leads to much more concrete efficient schemes that has fast and parallel provers and succinct verifiers. And the core technique behind this is this efficient lattice-based range proofs. If you have much better range proof, it leads to even better schemes and efficiencies. And I want to mention this is actually a very active area of research. There are many papers working on the lattice-based proof systems like SNARKs, polynomial commitments, and folding. And this is just an incomplete list, and there can be more papers. OK, so finally, I want to mention several open questions. I categorized the open question into two parts. The first part are those questions that I think is interesting, but I think if you put enough efforts, you should be able to solve that. That's my belief. But there's another category of challenges and open question, which I think is far more challenging, but also will be very meaningful. The first question is whether we can have some lattice-based non-interactive folding scheme without using Fisher-Shamir. Actually, we know this even in the elliptic curve setting. Like, you can understand Groth 16 as a folding scheme that requires no Fisher-Shamir, right? Because SNARK is a special case of folding. But we don't know anything about in the post-quantum setting. And I want to mention the key goal here is to just avoid this heuristic of heuristic, which I'm not comfortable with. As a practitioner, I'm comfortable with one heuristic. I'm not comfortable with the heuristic of heuristics.
If you compare it to Groth 16, they're assuming some like generic group stuff, right? So
I think algebraic, like
sure, but
I think I'm fine with knowledge assumptions and idealized model. Yeah, because I think if you want to have really practical schemes, maybe you need some kind of this kind of.
You prefer these over the random oracle?
No, I'm not prefer this over random oracle. I prefer this over heuristic of random oracle. This is not very good.
I mean, at the end of the day, random oracle will always be heuristic, right? At one point, it will be instantiated.
Oh, you mean?
So there will be two options, either scheme based.
By the way, this idealized model here is not random oracle model.
So what's the
the algebraic idealized model.
But in the lattice setting, it's not clear.
Yeah, that's an open question too. Yeah. And second is whether you can have a linear time prover for lattice-based schemes. For now, we don't have it, even though it's highly parallelizable. But sequentially, it's not a fully linear time. And this question is whether you have strict linear time folding that has log-sized verifier. This is something I think is already achieved by William and Ben, they have a strict linear time for hashing, which is really exciting, but we don't know.
Not because of the FFT.
Yes, the FFT O degree D. Yeah. Right. So the question is whether we can have linear time for that, which I don't know. Yeah.
Do we have any knowledge assumptions in lattices that are not broken?
I know some knowledge assumptions that are broken, and, but I think David mentioned to me that he's having some new assumptions, but yeah, I'm not sure.
I don't think they're broken in the practical sense. They're broken in the sense that also other knowledge assumptions are also broken, maybe in a slightly stronger sense. But if you look at lattice-based constructions of, say, designated verifier SNARKs, whose knowledge assumptions are broken, you can default to weaker knowledge assumptions. So again, I don't think that breaking the knowledge assumptions is a source of practical concerns. I think you have.
Is it because of like auxiliary information that they rely on the knowledge assumption?
I think it's more about the strength of the knowledge assumption. It's more nuanced than that. Yeah, but auxiliary information is of course also an issue for all kinds of knowledge assumptions.
Okay. Yeah. I think that's basically it. Thank you so much. If you have any more questions.
Close to on time. So any other questions?
How does the efficiency of your scheme compare to the following? So
compared to what?
The efficiency of your range proof. You decompose like each coordinate of the vector into 4 squares, and like for each like square, you use approximate proof to prove that there is no wraparound. So here, like you only do like 4 linear proofs plus like the sum of 4 squares.
You're comparing which to which? You're comparing
your range proof scheme.
You are compared to the second one or first one?
The first one.
First one with the second one, you're saying?
No, with the following. So you decompose each coordinate with 2 4 squares.
Oh, I see. You say basically I don't decompose L, I decompose smaller one. Mm-hmm. And actually it turns out that be even more expensive because in the zero check you have a much higher degree for the zero check. The degree, the function of G has a much higher degree than sum check will be more expensive. So there's some trade-off. It turns out in practice, actually, binary decomposition becomes or four-arity decomposition becomes the most efficient scheme. Because the zero check also has some cost for large degree.
We'll take this one.
Yeah.
Thanks.
Yeah.
So I have a bit of a historical kind of question, which is, the first proof system, if sum check, is a folding scheme if you think about it.
It's compositional folding scheme, I would say. Right.
Okay, and then we started with like folding schemes in some sense. Mm-hmm. Then there was like proof composition. Now you're like SNARKs and SNARKs and SNARKs, and now we're back to folding. Like what? I'm not sure what the question is, but what's the cycle like? Why?
It's too young.
Sorry, I guess it's a question maybe to Dan then. Like,
what you're saying, we're going to go back to.
Basically, what you're saying now is like, we started with folding, we abandoned folding, we went to snarking SNARKs or bugging bugs if you want, and now actually.
Well, the truth is they're used in different settings. Yeah, if you only have, if you need to have multiple provers, where one prover does part of the work, and then it passes on to another prover to do some of the work.
No, I'm not talking about that. No, I'm not talking about that. I'm talking about actually you have one big system, but it's easier to kind of do a little snark and a little snark and then do a snark and that because then the extensions are smaller. It's always easier to.
No, in that case, folding would be better.
Folding would be better.
Yeah. Well, we learned.
Yeah.
And also, I think the reason for this is because initially our goal is not for prover. Like our goal is for small proof sizes and small verifier. In that case, we have generated a lot of new schemes based on elliptic curves, pairings that is more complicated and have really small proof sizes. But as time goes by, suddenly we come back to the goal of having more efficient prover. And it turns out finally sum check is a really great tool for that. And we come back to the beginning of the life. Yeah.
And I guess like also sort of what happens in practice, right, is that again, this composition of like, okay, I want to have like really 2 proof systems that have sort of extreme properties. One with a really, really fast prover, and then I can just, like, if I also need a small proof size, I just throw that on top of it.
Yeah,
so
exactly.
It just turns out that I think like recursion is now practical and people do it, and like So that just opens up the door, and now we can optimize like for one parameter at a time, which turns out to be easier.
Good. Okay, great. Thank you.
Yeah.
So sort of naively to apply this to prove circuits, let's say one, it would be nice if the circuit was already structured in like little pieces. But if it wasn't, do we know of like some sort of using memory checking and such, like, can we convert this into like something that's amenable?
So yeah, I think for general circuit rather than structured circuit,
yeah,
there's a paper actually by me and Wilson and Dan Nirvan that allows you to convert this checking a general circuit into checking a like structured circuit. So there are actually even like more practical scheme for that. But theoretical wise, it's very easy, just using universal circuits. That's already easily solved.
But there is something called a uniformizing compiler that compiles any structured circuit to a uniform computation very efficiently, much better than a universal circuit.
Yes, that's what I said. Yeah.
Cool. All right. Thank you, Binyi. I guess we'll start again at 3:30.